All right, welcome. Today we are diving headfirst into what is basically a high-stakes geological detective story. We're on the hunt for a pure, uncorrupted sample of fluid from miles beneath the Earth's surface. And believe me, this isn't just any sample. It's one that can make or break a billion-dollar project.
So here's the core problem, right? I mean, just try to picture this. You have to somehow grab a perfect, pristine cup of liquid from a pipeline that's under insane pressure, it's scorching hot, and oh yeah, it's at the bottom of a 2-mile deep hole in the ground. It's a mind-boggling engineering challenge, and if you get it wrong, the consequences are massive. And this is exactly why it matters so much. You see, a good sample gives you a crystal-clear roadmap for how to develop the entire oil field. But a bad sample? Whoa. A bad sample is a disaster. It tells you to build the wrong multi-million-dollar facilities, to drill in the wrong spots. It sends you down a path that wastes hundreds of millions, if not billions of dollars. You really only get one shot to get this right. Okay, so let's start our investigation with our most common suspect, the one we run into all the time in the field, the classic oil reservoir. This is our baseline, you know? The case we have to absolutely nail before things start getting really complicated. Now, before we even think about taking a sample, we have to gather clues. We need to open up our detective's toolkit. We measure stuff like the pressure and the temperature way down in the well, and then back up at the surface, we're tracking exactly how much gas is coming up with the oil. Every single one of these data points is a clue that helps us build a profile of our fluid to tell us how it's going to behave. So, all those clues, all that data, it all boils down to one absolutely critical question. Is the pressure down in that reservoir high enough to keep all the gas completely dissolved in the oil, or has the pressure dropped to the point where that oil is starting to fizz? That exact threshold is what we call the bubble point. The best way to think about this is like a bottle of soda, right? When it's sealed shut, the high pressure keeps all that carbon dioxide totally dissolved in the liquid. You can't see a single bubble. But the second you twist that cap, the pressure drops, and instantly, poof, bubbles form everywhere. Well, for oil deep underground, that precise moment where it goes from a pure liquid to a liquid full of gas bubbles is the bubble point. Now, engineers aren't just taking a wild guess here. They use a specific predictive formula, a tool called the standing correlation. They plug in all that data we collected from our detective's toolkit, and this formula crunches the numbers and calculates the bubble point. It tells them if it's actually safe to go down there and grab a clean, single-phase sample. But what happens when the reservoir isn't filled with simple, well-behaved oil? What if it's holding something way trickier, something that literally changes its form as it travels to the surface? Well, in Section 2, we're going to meet the gas shapeshifters. See, gas isn't always just gas. You've got dry gas, which is simple. It stays a gas from the bottom of the reservoir all the way to the surface. Easy. But then you have wet gas and gas condensate. These guys are different. Deep underground, they exist as a pure gas, but as they travel up the well and the pressure and temperature plummet, they start to shapeshift, and some of that gas actually condenses into a super valuable liquid. And this, right here, is a huge problem, because at the surface, you get both gas and liquid coming out of the pipe for both wet gas and gas condensate reservoirs. Just looking at your well test data, you often can't tell them apart. So how in the world do you know what you're actually dealing with and what the right sampling method is? This is the golden rule. It's a fundamental principle of engineering caution. You always plan for the most complex, most difficult scenario you could possibly face, which, in this case, is gas condensate. Why? Because if you're prepared for that, you are prepared for literally anything else. So you might be thinking, why not just use the same simple sampling tool we use for the oil? Because for these fluids, it fails completely. When you try to capture a gas sample down in the well, some of it is guaranteed to condense into liquid right inside your tool. And that liquid is sticky. It coats the inside of the sampler, and you can never, ever get it all out. Your sample is now totally corrupted, it's non-representative, it's useless. And on top of all that, you just can't get a big enough sample for the lab to even analyze. All right, so we've met the straightforward oil and the shape-shifting gases. But our detective story has one last suspect, and this one is the most deceptive of them all. In Section 3, we're going to uncover the volatile oil imposter, a fluid that looks and acts just like a gas, but is secretly something else entirely. I mean, look at this. It's a nearly perfect disguise. Both have what's called a high API gravity, which just means the liquid is really light and fluid, and both have a super high gas-oil ratio, or GOR, meaning they produce a ton of gas for every little barrel of liquid.
Just based on the data you get at the surface, they can look absolutely, completely identical.
And here's the plot twist. Remember that predictive formula we trusted for our first case, the standing correlation? Well, it completely falls apart here. It's useless. It was never designed to handle fluids with this much gas in them. If you try to use it, it will give you a dangerously wrong answer, and you'll end up misidentifying a really valuable volatile oil as a gas condensate, a catastrophic mistake.
Okay, so we've seen the simple case, we've seen the shapeshifters, and we've unmasked the imposter. We get the pitfalls, we see the billion-dollar mistakes waiting to happen. So now, for our final section, how do we solve this puzzle correctly every single time? Well, it turns out there's one procedure that works for every single suspect. This is the master plan, the one-size-fits-all procedure that always works. First, you assume the worst, that you're dealing with one of these complex fluids. Second, instead of trying to sample down in the well, you take separate, very carefully measured samples of the gas and the liquid right at the surface. Third, you send those samples to a specialized lab where they are precisely recombined and analyzed. And that analysis, that finally definitively unmasks the fluid's true identity.
And that right there is the key takeaway. This conservative, play-it-safe, surface sampling first approach is the only way to guarantee you get a reliable, representative sample that's actually worth $1 billion. It completely removes the guesswork from the equation, and it protects the entire project from a massive error, no matter what secrets that reservoir is trying to hide from you.
So, the procedure works. That billion-dollar sample is safe and secure. But you know, getting it right isn't just about protecting an investment. It's about getting a pure, untainted message sent to us from the deep past. Every single perfect sample holds the chemical secrets of a long-lost geological world. And now, thanks to some careful detective work, we can finally begin to read them.